morning. This talk is a talk mainly about the classification of organic pigments by Raman Microspectroscopy. There's actually inorganic pigments included as well, and I'll go into both. First, I just want to start by thanking several people. We've been doing this work on pigments by Raman Microspectroscopy in our lab for, I don't know, the last 5 or 6 years. And fortunately, NIJ was kind enough to fund us to actually formalize some of this research and do it a little bit more systematically. Macron Research Institute has provided us some of our pigment samples. Ed Suzuki has been kind enough over the years to offer his advice and samples, and Scott as well. And Scott was the inspiration for some of this work and some of the classification work after his binder classification scheme. And Patrick Buzzini has done a lot of Raman work, and I have to thank everyone at Microtrace, especially Ethan Groves and Jennifer Herb, who have done a lot of the data collection and interpretation in this work. So pigment identification, just to go over real quickly, I mean, pigments are all around you, and this talk, I suppose, in the research focuses on automotive paint pigments, but it's really the Raman spectroscopy is applicable to pigments anywhere. And if you look around you, just about anything that's colored has pigments in them. The difficulty is that they're typically small, as you saw in Ed's talk. They're oftentimes, they're typically around a micron and often smaller, and they're generally encapsulated in a matrix. And they're present at a low concentration, and that makes analysis difficult. So a lot of different techniques have been used over the years with varying degrees of success, PLM and microchemistry initially, but IR, XRF, EDS, a variety of different methods. And as you can see by the fact that pigments aren't all that commonly examined in forensic casework, all these methods have various limitations, and Raman spectroscopy is no exception. But I think you'll see, hopefully, that Raman has some very interesting advantages. And as I say here, pigments remain really the only major part of a paint that isn't routinely identified in casework. So this is a PLM image. It doesn't look as good on there as it does on my screen, of a thin section of paint. And you can see there's some opaque pigments, the circled. This is a blue paint, but there's the opaque, dark opaque pigments down here are metallic flake. There's micas. There's blue. This is a larger blue pigment, but they go down even smaller than you can resolve. There's a green pigment here, which hasn't turned up very well, and there's red pigments in here. So in the single paint, just by light microscopy, you can see that there's a variety of pigments. So Raman microspectroscopy, I think now more than ever, it's been around for a long time. The Raman effect was discovered in, I believe, the 1920s. But in the last 10 to 15 years, Raman has become really a more mature analytical technique, and something that I think is a technique that's more easily applied practically in a forensic laboratory, because the systems have become more stable. There's a lot of vendors that supply them. And so for that reason alone, I think Raman spectroscopy has a lot of applications. It's great for in situ analysis. Rather than preparing samples, a lot of the Raman spectroscopy can be done by just putting a paint sample without any preparation, even through a clear coat in some cases, under the microscope or under a macro system, and you can get a good deal of information. With sample preparation, you can get even more information. It's fast, it's a small analytical volume, so in theory you can, with a confocal microscope, you can start to actually look at individual pigment clusters, maybe not individual pigments. It's non-destructive, and people generally, as soon as they hear about Raman, they learn very quickly that it's possible to burn samples. If you actually start with lower laser powers, in most Raman systems, laser power is adjustable, and work your way up, you can mitigate a great deal of the burning and lighting samples on fire that you've probably heard about. Fluorescence is really the big problem, and it will always, I think it will always be a problem. You can get around some of it by using different laser wavelengths. The further you go out towards the IR, the better off you are. We did almost all of the work with the 785 laser that we found to be very helpful or very useful. But if you go out even further, I'm told, and I don't have this equipment, but I'm told that that can avoid fluorescence even further. And besides just pigments, Raman spectroscopy has a lot of other applications for identification of unknowns in general. Drugs, many types of inorganics and many types of organic compounds can be identified by Raman spectroscopy. So I think it has a very appropriate place in the forensic laboratory. And in our lab, when we got our first Raman system, probably about 5, 6, 7 years ago, somewhere in there, we started applying it, not necessarily to be used in our reports, but we started applying it to every sample we could think of. And we found that it's incredibly valuable, and it provides a lot of complementary information to IR, but it also replaces or serves, in a lot of cases, almost like a micro XRD, X-ray diffraction, because you can get polymorph information that is sometimes harder to tell by IR spectroscopy. So to get to the actual project, pigment identification is a natural application of Raman spectroscopy, because whereas paint binders are great with IR, they don't really scatter Raman as well, and pigments do. And so when you look at a paint sample, pigments are what produce a great deal of the spectrum. And so over the last several years, looking at everything from writing inks to automotive paints and architectural paints, sort of in a scattered way, and collecting what pigment samples we could, NIJ provided us a grant to do this a little bit more systematically. So what we did in this year-long project was organize our pigment reference collection to include a lot more metadata and a lot more supporting data about the pigments. We did some basic reproducibility studies just to look at pigment heterogeneity, things like this. Look at the effects of laser. We'll get into that just a little bit. Collection of Raman reference spectra. This was probably one of the major focuses of the research. Verification of Raman reference data, and this is, I don't want to use the word authentication because it's not a full authentication, it's a verification. We'll go into that. And then development of a pigment identification scheme. And this is sort of the end product of this work, at least a first draft of the identification scheme. So our colorant collection at Microtrace, we've always been really big on collecting physical reference samples and having them and characterizing them, and it helps us to understand how to analyze materials better and how to apply analytical methods more appropriately. But we have over 1,100 pigments in our collection now, and you can see how it's broken down. We really focused, there's over 300 unique pigments, not including the effect pigments and the extenders. And we really tried to focus on not necessarily the artistic pigments, because those have been well classified. There's some overlap, of course, but we've really tried to focus on things that were of more industrial use. So, and everything's in a database that we started many years ago, and now it's sort of all filled out nicely. Before we go any further, I just wanted to go into naming a pigment, because there's a lot of names. I mean, in Ed's talk, he mentioned crystalline silica and diatomaceous silica, and there was one other one. I think maybe amorphous silica, I can't remember. But those are all sort of general names, but in the naming scheme, they all look like the same pigment. They're not actually separated. So the color index was started many years ago, and it's gone through 4 editions and now is available online as an online resource. But they're registered, and they're given a generic name and a constitution number. And so you have a trade name, something like burnt umber, brown umber, and that can be specific to a manufacturer. But the generic name, which refers to that sort of group of pigments, which can actually have multiple structures, multiple chemical structures, pigment brown 6 for this particular case. And then in theory, each structure is assigned a constitution number. So it sounds nice and straightforward. It's actually not when you start to look at the details. One pigment can have multiple constitution numbers. One generic name can refer to multiple structures. And then there are colon numbers that come after both the pigment brown 6 and after the constitution number. That adds further complexity. I'm not going to go into that, but it's interesting analytically nonetheless. There's a lot of other small little subtle differences that the color index people have encountered over the years, and they've dealt with it in various ways that aren't always consistent, at least analytically. So it's just something to be aware of. But this is the best way of naming pigments when you're referring to them as either pigment brown 6 or by the constitution number. That's a good way to do this. So our preparatory studies, we looked at sample substrates when you put your sample on different substrates. We looked at laser power effects. on samples. How do you choose a laser power? And what effects does changing laser power have on the sample? The biggest effect we noticed, first of all, the laser power effects were minimal. We did notice a little bit of peak shift and broadening with increased laser power, and that was really due to heating, and it was reversible. But it didn't really change your ability to qualitatively identify pigments, so it's not really important. We looked at day-to-day reproducibility of Raman spectroscopy over a period of the grant, just to show that things don't change outside of the resolution, at least for standard samples. And we looked at reference sample homogeneity. So we picked 5 common pigments, and we sampled them from throughout the pigment container to look, can we see differences in the pigment concentration by Raman spectroscopy? And the answer is no. If you look at some dyes and pigments in the workshop on Monday on pigment samples, we found there was a nice presentation. It discussed how when you analyze dyes by mass spec, a lot of times they're not pure, and you get a wide range of compounds that make up that color, supplied by a manufacturer. Raman spectroscopy is not sensitive to that, and it's kind of a nice thing actually for pigment identification. So collection of Raman reference spectra. We used a dispersive instrument to collect our spectra. We ended up collecting 275 organic and inorganic pigments, with over 200 of them being organic pigments. Multiple spectra were collected from each sample. So as we studied each sample, we tried to get this best possible spectrum. And sometimes that included sample bleaching, trying different lasers, different number of accumulations in different times. Since we had multiple samples of a lot of our spectrum, we didn't have time to collect data from all samples of a given pigment type. We developed a quality index rank, and this is based, here's a Raman spectrum from the collection. And we have, this is just anatase, it's one of the most common pigments. And we have basic information, basic analytical information down here about the spectrum. Laser power, acquisition time, bleaching time, number of accumulations, and then the peaks labeled. So this is part of our final report. The quality index we developed, it's a little bit based on the powder diffraction system, has a way of classifying their diffraction patterns as good or bad. We developed this as a way to rank the provenance of our pigments, because when you're trying to collect pigments, there's no one place to go to just buy pigments. Artistic pigments maybe, but we've acquired our pigments from a variety of sources, of which we know the source typically, but this allowed us to pick samples with the best provenance. Authentication or verification of reference pigments. The quality index gives us hopefully our best sample, but not always. And in looking at our data, and when you're collecting Raman data, you want to make sure you know what you're actually looking at. So we looked at them. Here's a PV20 example, PV23. 2 different samples, they were labeled the same, clearly different colors. What's the difference? Well, it turns out PV23 has different polymorphs, and we'll get into that in a minute. But they're not labeled, and a lot of times we don't get all the information from a distributor or even a manufacturer. So we attempted to verify. So we did visual comparisons. We collected EDS spectra of all of our pigments. And when necessary, we did IR or powder diffraction when we had reference samples. We also looked at the Raman spectra of similar compounds, or if we had multiple pigments of a sample, we sometimes analyzed multiple pigments to make sure we could compare them, or to see if they compared. And so these are the 2 PV23 samples. One of them actually gave a nice diffraction pattern, and from the literature, we were able to identify the polymorph, or the arrangement of the crystalline structure. Some common mislabeling, use of nonspecific common names by distributors or manufacturers. Hansa yellow is one example. Misleading trade names. Pigment gray and pigment turquoise don't actually exist. They're just generic, they're manufacturer names, but they're not CI recognized names. Mislabeling, curtailing of names by distributors was very common. And a lot of times the salts and specifics, such as the colon number, were not identified or weren't identified properly. So pigment red 49 is a calcium salt. Pigment red 49.1 is the barium salt. And this was labeled as 49.2. And I forget what 49.2 is, but it's not the, it's not the barium salt anyway. And some pigments were just flat out labeled wrong, actually, surprisingly. This was labeled as CI pigment white 6, titanium dioxide, and EDS, we have a huge silicon peak, and we look at the SEM image of it, and it's diatomaceous silica. You can see the biogenic fragments of silica. So on to the next step, pigment classification. The color index provides classification into 21 chemical categories. And that's a good start, but it doesn't always correspond well with the spectroscopic data or advances in chemistry that have taken place. So it's not always the best way to do this for forensic purposes. And so we developed our own classification scheme, and I'm not trying to take credit for it because it's really out of a lot of different references. We used some literature. This High Performance Pigments book was very useful, spectroscopic differences, and discussions with people in the industry and how they classify pigments. And so we ended up with 44 categories and subcategories, and then plus inorganic categories, which we found easiest to separate by the cation. Okay. The three main categories were azo, polycyclic, and other for organic pigments. And these are the categories that we ended up with. Then there were azo subcategories, so we can go further. And these were all played out by spectroscopic differences as well. So we developed this, so using the Raman data and this chemical classification scheme, we developed a first go at a pigment identification scheme. So if you have a Raman spectrum and it's a mixture of multiple peaks, multiple pigments, spectral searching doesn't always work well, we've found. And so to have a sort of a flowchart approach, and this looks very complicated, it's worked really well for the paint samples we've looked at. It's not perfect, it's a draft, but it starts off, you can do a pretty good job separating organic and inorganic pigments based on the strongest pigment peak into these two categories, based on the wave numbers. And then this goes just further down through peaks, and you can get to to a specific peak. The nice thing about this is when you're looking at a paint sample, a lot of times you don't have all the peaks that you would have in a nice reference spectrum. Not even a lot of times, all the times. Generally, you're limited to just a couple of peaks. And the nice thing about this table is not just for classification, but to know how far you can take an identification. Can you take it just to a group, beta-naphthol, or can you start to eliminate some of the pigments, such as, and so this whole scheme, which can be expanded to include more pigments in the future, but this whole scheme can allow you to know exactly how far you can classify your pigment. And that was one of the limitations when we were doing this work more scattered earlier on, is that we didn't know, do other pigment yellow 74 pops up on our spectral hit match? Well, are there other pigments that have a similar Raman spectrum or indistinguishable Raman spectrum? And this scheme should help to do that. And then we have some beta-naphthol pigments, or a pigment that fluoresces. And as a result, it's listed here so you know that it's there, but as a result, it doesn't give a Raman spectrum. And then we have pages that show comparisons of spectra with the peaks we use for classification in a given group so that you can actually compare them directly. And so all of this is put together in a 500-some page report that's being reviewed by NIJ right now, and it will be available for download, so everybody gets the benefit from this work. The benefits of this are large collection. It's a large collection that I think includes most commercially available pigments, at least based on our literature research. There's surely more that are not in there. Pigments are grouped by chemistry. The scheme is based on the strongest peaks. And I think the big thing is you can tell how far you can classify it. So one quick example, and then I'm done. A red paint, red automotive paint right here. And we can actually identify 3 different pigments, a yellow iron oxide, pigment orange 36, and pigment red 209. And we can specifically identify those pigments in the sample. A green architectural paint, we can identify only that it's a diarylide, not more specifically, a quinacridone and a Prussian blue. And so this is the end of the talk. The conclusions are listed. I've talked about all of them. So I appreciate you taking the time to listen to me, and hopefully this makes Raman a little bit more attractive as an alternative analytical method. Thank you.